Assalamualaikum and good morning to Doctor and my fellow friends. Today, we are from Group F, are present and will present our project entitled Web Production Performance. This project focuses on developing a web-based application that analyzes web production performance using production engineering concept and real-world data. The system is designed to help users evaluate web productivity more efficiently through automated calculation and clear data visualization. Before we begin with the technical aspects of our project, let me first introduce our team member and explain each person's responsibility through this project. Every member plays an important role in ensuring the successful completion of the project. As me, the project manager, Nur Faradiba, coordinate the overall project timeline and sign as a multi-member, manage and monitor the project progress to ensure every milestone and achieved on schedule. Next, our lead programmer, Wong Jiamin, was responsible for developing the core functionality of the web application using Python and Streamlit. He also implemented the engineering calculation and integrate the system logic into the application. Next is Mohammed Danish Daniel, served as a UI or UX designer. He designed a user-friendly interface, selected layout and color scheme, and worked closely with the programmer to ensure the design was successfully integrated into the application. Next is Alan Ellis David, as a QA and tester. His responsibility was to test the application thoroughly, verify the accuracy of all calculations, identify any error, and ensure the system performed consistently before the final presentation. And finally, Wan Alia Masara was our lead presenter. She prepared the presentation material, coordinate the presentation flow, and ensure the project outcome will communicate clearly to our team members each. Through effective collaboration, each member contribute according to their abilities, enable us to complete the project successfully. As you can see in the slide is illustrate the project timeline using a Gantt chart covering from week 8 until week 16. During week 8, we conduct our first meeting to discuss the project requirement and divide responsibility among team members. And week 9, we held our second meeting to finalize the project topic and determine the overall project direction. Between week 10 until week 11, we focus on collecting and studying real field production data from published research papers related to inflow performance relationship IPR and vertical lift performance VLP analysis. Starting from week 10 until week 14, our lead programmer developed and the web production performance analysis using a Python and Streamlit, including the implementation of engineering calculation and the web interface. During Web 12 to Web 15, the system evaluated data insertion, functional testing, debugging, and validation to ensure the application operates accurately and reliably. Finally, in week 16, the entire team collaborated to prepare the presentation slide, record the demonstration video, and finalize the project for submission. Overall, the project was complete according to the planned schedule, with each milestone achieved within the allocated time frame. Next, I will give to my friend.
To elevate well performance, we use nodal analysis. This technique measures the reservoir delivery capacity, which is the inflow performance relationship IPR with the wellbus lifting capacity and the retrieving performance relationship TPR to determine the well's optimum operating point. This operating point is representing the thermodynamic equilibrium of flow rate and bottom hole pressure. Our framework is drawn directly from well-established case studies in petroleum production engineering by Buyon Guo, William Jones, and Ali Galambov, published in 2007. The validated dataset extract from this literature contains critical operating parameters. This include the reservoir pressure, well depth, gas liquid ratio, and wellhead pressure. These combined data elements define the mechanical limits of the well system. This data we use to validate the calculation generated by the web application.
Today, I will go through our flowchart for evaluating the web production performance. So the systematic workflow allows us to perform the nodal analysis by integrating the reservoir deliverability with wellbore hydraulics to determine the optimum operating point of the well. So start the phase 1, we begin the process by collecting the input reservoir data such as the reservoir pressure, test flow rate, and the bottom hole flowing pressure. So we require this data to calculate the productivity index, which is the PI. So the PI is represent as the well ability to deliver fluids and calculate as the test flow rate divided by the drawdown pressure. Once we obtain the PI, we calculate the maximum flow rate, which is the Qmax. So the spherical absolute open flow potential occurs when the flowing bottom pressure drops to 0. And it's calculated by multiplying the PI by the static reservoir pressure. So next we generate the flow rate values range from the 0 up to the calculated Qmax. So we calculate the corresponding PWF using the straight line PI relationship where PWF equals to PR minus Q divided by the PI. So we plotting this coordinate, which allow us to successfully generate the inflow performance relationship IPR and using the PI method, which visualizing how the reservoir delivers fluid to the wellbore. So now that the reservoir site is established, we shift our focus to the wellbore lifting capacity. We include our VLP method 1 parameter, which include the gas liquid ratio, GLR, tubing head pressure, THP, tubing depth, and the fixed tubing size of 2.875 inches. We use this parameter based on our VLP database, so we can determine the THP and PWF equivalent depth. This data allows us to compute the pressure loss due to friction and gravity inside the tubing string. Finally, we can generate the VLP curve and plot it to the same graph as our LPR curve. So the intersection point we call as the actual operating point, which show the specific flow rate and flowing bottom pressure that well will produce under the current configuration. So this performance analysis is ensure production is optimized. Next, I will pass to my crew members for the process.
All right, now we go to the field data. So this is the data that we use to test our website. And this data we find from the case study of the Shen 77 well of the Leon Shihang Altil. And the reference for this data, as you can see at below, is from the Advanced Well Completion Engineering third edition. So the specific data that we use to test our website is the reservoir pressure, reservoir depth, bottom hole flowing pressure, the flow rate, the GLR, and the wellhead tubing pressure. And for the tubing size, our website only focuses on the 2.875 inches. And the other additional data, as you can see here, is just the additional data that we found from the case study. Right, next. Now, before we plug in or put our data to test our website, so we need to convert all the data into a standard feed units. So like the pressure, we use PSI, the GLR, we use MCF/PBL, the depth you use in feet, and the flow rate you use in PBL per day. All right, next. I will now pass on to my friend Wong Jiaming.
Okay, thank you, Alan. Good day to Dr. Rahim and everyone. My name is Wong Jiaming, and I am the lead programmer and backend developer of our project. After understanding the production data of the Shen 77 well and converting it into field units, the next step is to perform the engineering calculations and determine the operating point. Instead of carrying out these calculations manually every time, our team developed a web-based application that automates the entire process. The objective is to provide petroleum engineers with a faster, more convenient, and more friendly user platform for analyzing well production performance. Today, I will demonstrate how our application works using the actual production data of the Shen 77 well. So this is the home page. Okay, this is the home page of our application. The application consists of two main calculation modules. The first module you can see is the IPR, inflow performance relationship, or IPR, while the second module is the vertical lift, you can see vertical lift performance, or VLP. Together, these two analyzers enable us to determine the operating point of the well. So let us begin with the IPR calculation. For the IPR module, the application requires three input parameters. The first is the reservoir pressure. In the first, you can see here. Okay, so we will key in 2,364 psi. Okay, we press enter. Next is the test production data, which is 345.5 barrels per day. Finally, we will enter the bottom hole. We enter the bottom hole flowing pressure, which is 1,600 psi. After, behind the scenes, the application will automatically compute the productivity index, followed by the maximum production rate using the productivity index method. It then generates the complete IPR curve without requiring any manual calculations from the user. This greatly reduces the calculation time for minimizing the possibility of human error. So you can see here, this is our updated, the blue line IPR curve is the updated one. So next, we move to the vertically performance module. Unlike the IPR calculation, the VLP analysis considers the pressure losses like just now Alia mentioned, encountered while transporting fluids from the reservoir to the surface through the production tubing. For this module, we first select the gas liquid ratio where we will use 0.6. Okay, you can see here we have start from 0.0 until 0.8. The unit is in 1000 SCF per barrel. So we will choose 0.6. Okay, and then so next we choose the QV head pressure for the Shen 77 valve. The reported value is 638 psi. However, the Google chart currently implemented in our application provides pressure data at 500 psi interval. So you can see here 500 psi interval start from 500 psi until 2500 psi. So for this demonstration, we use the nearest available value of 500. So you click on the 500. Next, we select the tubing depth. The actual well depth is 5,489 feet. While the current version of our database supports value up to 5,000 feet only. So we will use the closest available depth of 5,000 feet for this analysis. So you can see there's several options for the user to select, start from the 1,000, 2,000, 3,000, 4,000, and finally it's 5,000. So we click on it. So after selecting these parameters, the application will automatically retrieves the corresponding pressure values from the digitized Google chart database, where it is completed by our team in an Excel file. So and the application will repeat the calculation for multiple production rates before generating the complete vertical lift performance curve. So you can see here. We'll start from the flow rate. We'll start from 50, 100, 200, 400, and finally 600. These five flow rates are the available flow rates in the Google chart. Okay, so finally, our application overlays the IPR curve. This is the IPR curve, and then the VLP curve on the same graph. Okay, so you can see the point where these two curves intersect. You can see the orange color point is the operating point. This point represents the equilibrium condition where the reservoir inflow exactly matches the tubing outflow. In other words, it indicates the production rate and bottom hole flowing pressure at which the well can produce under stable operating conditions. So you can see the flow rate will be 430.37 barrels per day, and the bottom hole flowing pressure is 1,412.33 psi. So instead of manually plotting multiple graphs and identifying the intersection visually, our application performs the calculation automatically and presents the result immediately. Besides improving calculation speed, this application also serves as an educational tool. Students can clearly visualize how changes in reservoir pressures, tubing head pressure, the gas liquid ratio or GLR, and the tubing depth influence the operating point and ultimately affect the well productivity. For practicing engineer, the application can also reduce the repetitive manual calculations during preliminary production performance analysis. So, like any engineering software, the current version has several limitations. At present, the VLP database supports tubing head pressures at 500 psi intervals and tubing depths up to 5,000 feet. Consequently, the Shen 77 well requires the nearest available values rather than the exact field measurements. Future improvement will incorporate interpolation techniques and a more comprehensive Google chart database, allowing the application to represent the real field conditions with greater accuracy. In summary, our web application successfully integrates the productivity index method with the VLP method into a single user-friendly platform. By combining engineering principles with software development, it enables users to rapidly evaluate well performance and determine the operating point using real production data. So I want to thank you for your time and also attention. That's all from us. We are Group F. Okay, thank you very much.